Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abutiwa Sos, Ugobela Maths. And without any further ado, let's look at these questions that we have here. Okay, so we have question 6 on chemical equilibrium. It says the following reaction reaches equilibrium at a temperature of 327 degrees Celsius. Then we have that reaction there given. Then 6.1.1 says, what is the meaning of the double arrow? So we know that double arrow there means that this is a reversible reaction, right? So that's what you tell them for a mark. It's a reversible reaction. Then, okay, now they say, how does the rate of the forward reaction compare to the rate of the reverse reaction during the following time intervals? Choose from higher than, lower than, or equal to. Then we are given 6.1.2 before equilibrium is reached for the first time, and then also 6.1.3 when it is at equilibrium. So this here refers to this graph here that we have like that. And then if we have the rate versus time graph, we know that the rate versus time graph is always in this manner, whereby we have our forward reaction starting up there, and then we have our reverse reaction starting down here, right? So at a certain point, they then have the same rate, but then note here, this is the forward reaction, and then this is the reverse reaction. Now from this graph, we can tell that before equilibrium is reached for the first time, remember, T1 here, let's say this is when equilibrium is reached for the first time. So before equilibrium is reached for the first time, you can see that the forward reaction is the one that is above the reverse reaction, which means that the rate of the forward reaction is higher than the rate of the reverse reaction. So for 6.1.2, we are supposed to say it is higher than. But then as soon as equilibrium is reached, what happens? This is at equilibrium starting from T1. So let's indicate maybe T1 to T2. Let's say this is equilibrium. So at equilibrium, we can see that the rate of the reverse reaction will be equal to the rate of the reverse reaction. So rate of forward reaction is equal to rate of reverse reaction at equilibrium. So here we are supposed to say equal to. So all that is based on this graph here. Okay, then let's proceed. Okay, so the reaction is started by placing 4.88 moles of N2 and 6.18 moles of H2 in a 2dm sealed container and allowed to react. When equilibrium is established at 227 degrees Celsius, it is found that 41.48 grams of NH3 is present. Then 6.2 is saying calculate the equilibrium constant Kc at 327 degrees Celsius. Now what you are supposed to do here is to use your Rice method, which means R here, the first R is for your ratio, and then the I is for the initial number of moles, and then we have C, which is for the change in the number of moles, and then we have E here, which is equilibrium number of moles, right? And then the last block, remember, it is for the concentration at equilibrium. So this one is representing the concentration at equilibrium. Now, how you go about with this one is that you know that for the first block, so you always put them in that order. So you have your N2 here, you have your 3H2, and then the product here is your 2NH3. Then for the ratios, you're just gonna fill in your coefficients here. So the coefficient of N2 is 1, the coefficient of H2 is 3, and then the coefficient of NH3 is 2. So those represent your ratios. So the coefficients that we are seeing here, they represent our ratios. Then now from reading here, we are told that the reaction is started by placing 4.88 moles of N2. And then that's the initial number of moles because it is started by placing that. So that's initial. So we have 4.88. And then we have hydrogen. Hydrogen gas, they place 6.18, right? And then we know that at the beginning of the reaction, we won't have any product, so that means the number of moles of the product is just 0, right? Then from here we are told that when we read further, we are told that when equilibrium is established, meaning at equilibrium, it is found that 41.48 grams of NH3 is present. Now we cannot take the 41.48 grams and put it here because remember we are looking for the number of moles of the at equilibrium, but here we are only given the mass, right? So what are we supposed to do? That's when we use our stoichiometry and say, okay, let's calculate the number of moles of the NH3, which will be the number of moles at equilibrium, by saying this is mass over the molar mass. Now the mass we are given is 41.48, and then the molar mass of NH3, we know that nitrogen is 14 grams per mole according to our periodic table, and then our hydrogen is 1 gram per mole, but there is 3 atoms of that hydrogen. So all in all, we get 14 plus 3, which is 17, right? Now 41.48 divided by 17, that will give us 2.44 mole, right? Then what do we do with this one? We're going to put it here. At equilibrium, remember that number of moles was found at equilibrium. Now that means we can be able to calculate this one, because to calculate the number of moles at equilibrium for a product, it's always I plus C and then equal to E, right? Note that this is when you calculate for the product. So that means in order to find the equilibrium here, it has to be the number on the initial plus the number on the change to get this one. Now, obviously, the number that we can add to 0 to get 2.44 is obviously 2.44. Now, at this point, you need to note that in order to get the values of the other compounds or the other substances, that's when we start to use the ratios. So the change block relates to the ratio. So every time you want to find the values in the change block, always note that change relates to the ratio. So how do we find that? If we want to find the number of moles of the hydrogen gas, then we should compare the ratios here. And then this is a rule of thumb. This is how you do it, guys. So you will take the number from here, multiply by the ratio on the H2, then divide by the ratio of the NH3. So you get that. So that means that's a 2.44 multiplied by 3 and then divided by 2. Right, so it's this multiplied by that divided by this. And then when you punch that in your calculator, you get 3.66. Right, and then again, when you want to find this one for N2, it's this number multiplied by the ratio of N2 divided by the ratio of NH3. So note that. This multiplied by that, then divided by the ratio of NH3. So if you say 2.44 multiplied by 1 divided by 2, then you get 1.22. Okay, so now this is what you need to note. Remember, I just told you that in the product side, if you want to find the number of moles at equilibrium, you say initial plus change is equals to E. But what about if you are now on the reactants? Note that we have 2 reactants. Your nitrogen gas and your hydrogen gas are the reactants. So every time you are looking for the number of moles at equilibrium, then it says I minus C is equals to E. So it's the initial minus the change and then equilibrium. So always these ones happen when you are dealing with the reactants, right? So for the reactants, in order to get the one at equilibrium, I need to say this minus that. Right, so note this, very crucial for you to understand that. Right, so 4.88 minus 1.22, you get 3.66. Then 6.18 minus 3.66, you get 2.52. right? And then now it's time for us to calculate the concentration. Now, to calculate the concentration, you always have to note that your volume there will be given. Remember, we highlighted here and then we said the volume we were given as 2 dm cube. So that means after you have found the number of moles at equilibrium, then you take all this number of moles, you have to divide them individually by 2 so that you get the concentration. Remember, it's N over V. So to find the concentration, it's number of moles divided by the volume. So if we say 3.66 divided by 2, we get 1.83. We say 2.52 divided by 2, we get 1.26. We say 2.44 divided by 2, we get 1.22. Right. And then at this point, it's just a matter of having to calculate your Kc value. So allow me to just erase here. Hope you noted that, but you can always pause the video and recheck. Then, okay, so this is Kc is equals to, remember, what is Kc? That's the concentration of the product divided by the concentration of the reactants. As our product, we only have the ammonia, the NH3. So we have NH3, but then remember the ratio or the coefficients, they act as your exponent. So we have NH3, and then that ratio that becomes an exponent. So exponent 2 over, and then we have a H2, concentration of H2, and that ratio there acts as an exponent, right? And then lastly, we have concentration of nitrogen gas, and then that ratio there, it's 1, it acts as an exponent. So we know that an exponent of 1 wouldn't change anything, right? So even if you don't put it there. Now, as soon as you substitute in the values, note that we no longer use the square brackets. We now have to use the round brackets. So what is the concentration of NH3? There is it 1.22. But note now I'm substituting in the round bracket. So 1.22, and then we have to the exponent of 2. What is the concentration of hydrogen gas? That's 1.26. So I have round bracket 1.26 and then cube. And then from here, what is the concentration of N2? I have a 1.83. Now, all that's left to do here is to take your calculator, punch all this into your calculator, then you have your Kc. So your Kc rounded off to 2 decimal places is 0.41. And note that there are no SI units because Kc is simply just a ratio of the concentrations of products and the reactants. So there are no SI units for that one because it's simply a ratio. Right. So that's how you would have calculated your Kc for a total of 8 marks. So always note that. So make sure that you play the video as many times as possible and just try to understand the approach there. Okay, so now we have 6.3. 6.3 says write down the name of a factor that affects the value of Kc. Note that the value of Kc, right? So we know that your pressure, your catalyst, your what you call it, your pressure, your concentration, and also as well as your temperature. These three can all affect the position of the chemical equilibrium. But only one of these factors here, only one factor from these 3 factors can actually affect the value of the Kc. Note that the value of the Kc can only be affected by temperature. So the factor that can affect the value of Kc is the temperature. So that means this one is capable of changing that ratio value there. But these other ones cannot change the ratio value. They can only shift the position of the chemical equilibrium. But then they cannot shift, they cannot change the value altogether. But the temperature is that one factor that can change the value of the Kc. Okay, so now we have 6.4. It says the graph below shows how the percentage yield of NH3 varies with pressure at different temperature values, right? So we have a graph of the percentage yield of ammonia versus temperature. Now they say which graph A, B, or C represents the percentage yield values obtained at the highest pressure. Is it A, B, or C? Now this comes from knowing this, right? So if they're saying at a highest pressure, let's note an increase in pressure. This is what we know. An increase in pressure, according to our Chattelier's principle, we know that an increase in pressure will always favors the reaction that produces less number of gas moles, right? So always less number of gas moles, right? Now, in that case, we can see here, having to compare this, obviously we have to compare the sum of the ratios. So we have 1 here and then we have 3, meaning the sum of the ratios from the left-hand side is 4, but the sum of the ratios on the right-hand side is 2. Remember this one coming here, this is the forward reaction. So the forward reaction has 2 moles or 2 gas moles. And then from there coming to that side, that's the reverse reaction, meaning the reverse reaction has 4 gas moles, right? So which one has the less number of gas moles? It is obviously the forward reaction. So once that thing is on the product side, then it's the forward reaction. And once we are going to the reactant side, then we say it's the reverse reaction, right? So if we are going to the reactant side, it's reverse reaction. If we are going to the product side, it's the forward reaction. In this case, if we are saying an increase in pressure favors the reaction that produces less number of gas moles, that means in other words, the forward reaction is favored. So we say the forward reaction is favored. Now, obviously, if the forward reaction is favored, that means the graph that will be producing the highest yield of NH3 would have to be the graph that represents the percentage yield that is obtained at the highest pressure. Because if we are saying that if we increase the pressure, we favor the forward reaction, that means if we have to further increase the pressure, that means we'll be getting more yield of the NH3, we'll be getting more products, right? Remember, favoring the forward reaction means that we are promoting the formation of more products, right? So that means, in other words, in graph A, so we'll say in graph A, the yield of NH3 is the highest. And then thus the graph that correctly represents the yield at the highest pressure is A. Right? So that's how you do it. So obviously, you would have written here that the answer is A. And then how do you explain it? An increase in pressure favors the reaction that produces less number of gas moles. The forward reaction is favored in that case. In graph A, we can say that the yield of the NH3 is the highest, right? So this is the one that produces the highest yield of NH3, right? And then thus the graph that correctly represents the yield at the highest pressure is A. Now 6.5 says, what effect will the following changes have on the yield of NH3 at equilibrium, right? So what effect will it have on the yield, right? Remember our reaction there, our chemical equation, balanced equation was like this. So the 3H2 and then reverse reaction to give us 2NH3. Now let's base it on that. If they're adding more N2. They're saying more N2 is pumped into the container. So that means this is an increase in concentration. Remember, if they're adding more of that substance or they're adding more particles of that substance, that means that they're increasing the concentration. Now, remember, what do we know from our chemical equilibrium? If we increase the concentration of a reactant, then the forward reaction is favored. If the forward reaction is favored, that means there will be an increase in the yield of the product. There will be an increase in the yield of NH3. So we are supposed to say for 6.5.1, that means there will be an increase. Then 6.5.2, they're saying what will happen now if a suitable catalyst is added, right? If we add a suitable catalyst, will this affect the yield of the NH3? Not at all. Remember, a suitable catalyst, the only thing that it will do is just speed up the chemical reaction, but then it wouldn't necessarily change the yield of the NH3. So we say no effect. No effect. Then 6.5.3, the volume of the container is increased at constant temperature. Note, they're talking about the volume, but then we know if they are increasing the volume, we know that the relationship between volume and pressure is inversely proportional. An increase in volume means a decrease in pressure. And then according to our Chattelier's principle, we know that a decrease in pressure will have to favor the side with more number of gas moles. More number of gas moles. Now, in this case, if we are favoring the side with more number of gas moles, here we have the sum of coefficients is 4, and then here the sum of coefficients is 2. That means now we are favoring the reverse reaction. If we are favoring the reverse reaction, what will happen to the yield of the NH3? The yield of the NH3 would have to decrease, because remember, what is a reverse reaction? A reverse reaction is a reaction that promotes the using up of the product to form back the reactant. So that means we'll be using up the NH3 to actually form those reactants, and thus the yield of NH3 would have to do what? Decrease. So we say decreases. Right. That's how you go about tackling those questions. So make sure that you understand the concept there.